In this module, we will introduce ourselves to the concept of a total differential. This concept is where multivariable calculus starts to get both interesting and also a little bit confusing. So let's work through this carefully and make sure to go through the exercises also in a careful manner. So in order to first understand what's a total differential, let's just look at what does it mean to talk about a differential that is without the word total in it. So for this, recall that for a function of one variable f of x, we introduce the first derivative as given by df by dx. We could write down a trivial equality where we write down df by dx on the right side as well. There is nothing profound here. We have just written the same thing on both sides. But now we can do something simple, which is to take df by dx and multiply it by dx on both sides, but cancel out this dx only on the left side and not on the right side. So if we cancel it out on the right side, we are left with a df on the right side. In other words, this gives us df is equal to df by dx multiplied by dx. This df, which we have, so far we have only seen df by dx. We have never seen terms such as simply df, but for the first time we are seeing a change in f. We are not, if you just look at this quantity in the red box over here, it is not talking about how much did x change by, it is just talking about change in f. This quantity has its name, it is called as the differential of f. So you can think of the first derivative df by dx as a proportionality constant which relates the infinitesimal change in the function df resulting from an infinitesimal change in the variable dx. So we can think that df is proportional to dx, where the proportionality constant is df by dx. So now let's try to extend this concept to a multivariable function where we have f of xy, and it will be easy to generalize it to a function where we don't have just one variable, but as many variables as you wish. So for a multivariable function, we can similarly write df something proportional to dx plus something proportional to dy. What is it that is proportional to dx? Instead of df by dx, now we will have a partial f by partial x plus partial f by partial y. You might ask, how did this equation come by? It is the definition of df. There is nothing, it's not a derivation. This is the definition of the differential of f. And now since we have different variables in this case, its name is slightly different from what we had for the one variable case. This is now called as the total differential of f. So it's a straightforward generalization of the 1D case, and basically it tells us that the total change in the function df is the sum of change in f resulting from a change in x proportional to partial f by partial x plus change in f resulting from a change in y proportional to partial f by partial y. We can extend this to arbitrary dimensions. In arbitrary dimensions, we have f of x1, x2, up till say xn. And in this case, we will have df is equal to summation k is equal to 1 to n partial f by partial xk multiplied by dxk. And it's the same idea as in two variables. So now let's look at examples of what this total derivative means. Let's consider a function of two variables, volume of a cylinder as a function of its radius r and height h. So we have a cylinder that looks something like this. We have a height h and we have a radius r. So we can calculate the rate of change of volume if the height was kept constant. So first of all, we need to know what is this function. This is something which you should recall from, I don't know, high school geometry or first year freshman math, something like that, that it's a pi r square h. If this is confusing to you, you can go look up the Wikipedia page for the volume of a cylinder. So we can calculate the change in volume with respect to R if H is kept constant. That will be 2 pi R H. We can similarly calculate change in volume with respect to height if R is kept constant, and that will be pi R square. So what does this top thing mean? It means keep the height constant and allow the radius to change by a very small amount. How much would the volume change by? For that much, divided by that much change in the radius, it will be 2 pi RH, and similarly for partial V by partial H. So now we can write down the total differential of V, that will be dV is equal to partial V by partial R H. And this reminds me over here what is left constant. So here y is kept constant and here x is kept constant, and in this case all x1 x2 xk minus 1 xk xn are kept constant. Everything else except xk is kept constant. Only xk changes. So that becomes important. For example, in thermodynamics, a lot of mistakes can be made if you're not careful with what is actually kept constant. So here we have only just two variables. Life is simpler. This will be partial V by partial H at constant R multiplied by dH. And we can plug in the expressions we just wrote above. This will be 2 pi R H dr plus pi R squared dH. So what does this mean? This means that if you change the radius of the cylinder by dr, and at the same time, if you change the height of the cylinder by dh, the total change in volume of the cylinder will be 2 pi rh dr plus pi r squared dh. This is a simple but extremely important concept, and we will revisit this in subjects such as physical chemistry many, many times. So that's our first introduction to total derivative. Now let's try to see how can we extend a directly related concept to this is the chain rule for multivariable functions. So if you recall, the chain rule is interested in things such as when f is a function of x, but that x itself depends on something else u, and we want to characterize the change in f not with respect to x, but with respect to u. So that allows us to, this is a composition of functions, and there we know what to do. We can say df first with respect to x multiplied by dx with respect to u. Here, the only change is we don't just have x of u, we have some y of u also, and we have some z of u. So the f is a function of x, y, z, and x, y, z themselves depend on u. So in this case, f is a composite function of u. So now we want to understand how does f change with respect to u? What is the dependence? So for this, we can write down, first let's write down the total derivative of f. For this part, we can ignore that there is any dependence on u. We can just treat it as if there are three variables x, y, z. So we know the formula for this. This will be partial f by partial x, and here y, z are kept constant, plus partial f by partial y multiplied dx. X, z are kept constant multiplied by dy, plus partial f by partial z, x, y are kept constant multiplied by dz. Now comes the interesting part. Now we realize that we can write down dx as dx by du multiplied by du. Why can we do this? Recall, we did exactly something like this in this step over here. That's what we are repeating. So dx can be written as dx by du multiplied by du. Similarly, dy can be written as dy by du multiplied by du, and same thing for dz. The reason we can do that is because x is a function only of one variable. There is nothing complicated here. So writing dx, So dx itself is a total differential, right? But if it's a function of one variable, we can skip the total part. It is just a differential. So if we use this formula, then we obtain df is equal to partial f by partial x dx by du plus partial f by partial y dy by du plus partial f by partial z dz by du, and the whole thing is now multiplied by a du. So notice what we have achieved here. We have gotten rid of just dx. We have dx playing a role in calculating the derivative, but at no point we are looking at how much did x change by. We are only looking at how much did f change with respect to change in x, or x change with respect to u, but the only infinitesimal changes that we are looking at are f and u. So we can do this for a simple example and see how it works. For example, let's consider the composite function where u, capital U, is a function of x of t and y of t. So u is a function of x and y, but x and y themselves are function of some variable t. And this function is defined as x square of t plus y square of t. We still don't know what is the dependence of x on t, so that we specify now. X of t itself is sine of t, y of t is cosine of t. So now let's use this formula here for u and see what is the total derivative. So you can see that du is partial u by partial x dx by dt plus partial u by partial y dy by dt multiplied by dt. So we don't have a third term here because instead of x, y, z, we have only x and y. We can calculate du by partial u by partial x is 2x. So that gives us 2x. dx by dt is cosine of t. Partial u by partial y is 2y. dy by dt is minus sine of t. Now we can put in the formula for x as a function of time, that is sine of t. So this thing becomes 2 sine of t cosine of t, and y is cosine of t. So again here as well we have 2 cosine of t multiplied by sine of t. We get a 0. That's interesting. But now if you go back and take a look, it's not surprising at all, because indeed u is sine square of t plus cos square of t, which is a constant, which is equal to 1. So you could have guessed that result beforehand, that of course if u is a constant, du will be 0. So it's not surprising, but it was nice to actually see how the formula works, and hopefully this gives you some intuition into the thing. Let's look at one more example before we wrap up this module. It's not just an example, it's actually a bit more than that. What it says is to look at composite functions which are f of x t, y t, but now you can think of it as a special case where z of t is just t. So it's a subcase of the general case we just studied, but it's quite useful. It happens a lot. For example, you could have a function which is given, for example, this could be something given by e to the power minus t x plus y. So let's say you have x which is varying with time, y which is varying with time, and on top of that you have an exponential decay. So you have sum of two time-dependent things, and their sum itself is modulated through an exponential decay. These type of examples show up a lot in physical chemistry, in physics and chemical physics. So here we can write down the total derivative as df is equal to partial f by partial x dx plus partial f by partial y dy plus partial f by partial t dt. Now let's do the same thing as we did earlier and think about the change let's introduce a dt everywhere. So this becomes partial f by partial x dx by dt. So what we are doing is to multiply and divide by dt. This one becomes partial f by partial y dy by dt, while this one becomes partial f by partial t dt by dt. Dt by dt is simply 1, right? So this thing is simply 1. So we can write this as t partial f by partial t plus partial f by partial x dx by dt. Again, we're not doing really anything new over here. We are just taking the general case of composition of functions, but looking at a specific example where the third function is the parameter itself is time. It could have been time squared, then this wouldn't apply. It's just time. That's when, or some other variable. Typically, this happens with time. So that's why we are using the notation t. It doesn't have to be only time. So yeah. So that's what we have. And now we can bring the dt over here and we can write df by dt is equal to this thing. This is a very important relation. And this df by dt is now called the total derivative. So these were the two things we wanted to really look at in this module, which is total differential and total derivative. I will write it down clearly over here. So we saw the concept of a total differential. The total concept of a total derivative happens when you have a composition of a function and the third one of the functions. It doesn't have to be 3 functions. It could be 2 functions also. Just with one function, it won't make sense, but it could be 2, 3, 4, 5. Here I showed for 2. You could have done a similar thing for f of x t comma t. You would have a similar relation over there. So this total derivative is very important anytime you have a change in a system and many variables are changing. A function depends on many variables which themselves depend on some parameter, and the function itself has a dependence on this parameter. So let's look at the example which we wrote above, this one. And here, let's say that x is equal to sine of at and y is equal to cos of bt, where a and b are constants. So in this case, you can plug in through the math and you will see that df by dt comes out to be e to the power minus t sine of at plus cos of bt. I recommend that you work through this and make sure that you're getting the same result as what I wrote over here, and otherwise you're missing something. So consider this as an exercise for you to finish. A cos of at minus b sine of bt. So this is just an example, but what did we do here? What's the whole concept of df by dt? So the total derivative provides us a measure of the rate of change in the function resulting from a change in time, including direct dependence of that function on time. So this is the direct dependence of that function on time, but that is not the only way through which that function depends on time. It also depends on time indirectly. And it depends on time indirectly also. And once again, for the nth time, I keep saying time, because that's where you will see this happen a lot, but it's much more generic. It could have been some other variable. And in fact, in physical chemistry, we will see lots of examples where t is any variable that you want, and you will become comfortable with it. For now, just because it's written t, I use the word time, but I should call it t. So it has a direct dependence on t, and it has an indirect dependence on t. And the total derivative captures the rate of change of that function with respect to t, coming from both of these contributions. And that's what we derived here for this function, for example. That brings us to the end of this module. Thank you very much.